gives me great pleasure to be here, and I got tired of not being able to travel, and I got tired of virtual talks and all that. I love meeting people, whether they are young or old, or people previously known to me or not, and so on. And so for me, it was like being put in jail kind of situation with all this COVID-related restrictions. And even when I was doing my half-a-year stint in NUS first half of last year, I couldn't travel out of Singapore, and even locally, hardly anybody showed up in person and so on. Although my course that I taught, a seminar course, was an in-person course, but not too many people registered for it and so on. So I was getting a little tired of virtual way of doing business, because I strongly believe that in-person is still the best way to get to know people and get enthusiastic about stuff and so on. So no amount of virtual video, this, that can be a complete replacement for in-person way of doing things. So I want to point out a couple of things here. This QR code is for this URL, and the other one is for my home page. If you go here, you'll find tons of material, links to PowerPoints and videos and of talks, as well as even interviews and such. You will see some of the things that Eric mentioned in terms of the areas of work I've done. The other one has a lot more of links to my social media accounts and links to papers across the whole 41 plus years now of my post-PhD career. December 81 is when I finished my PhD at UT Austin and joined IBM Research in San Jose. Since some of you might not know, the lab I was at for 38 and a half years is where Relational was born. Ted Cord was my colleague even for 2 years after I joined, and then he retired. SQL came out of the System R project, and so one of the fathers of SQL, Don Chamberlain, was there till about 2005. Unfortunately, the other guy, who was also the main guy behind SQL, very early on in his life passed away, so I never even got to meet him. So even before System R ended, I think he died. And I joined midway through the R-Star project, which was a follow-on to System R, which was a distributed database version of System R. And the person who hired me, Patricia Selinger, she's considered the mother of cost-based query optimization. So I come from this kind of a place with a lot of history to it. Ron Fagan is still there. He's one of the theoretical database guys, right? Fourth normal form and such things. And Jim Gray used to be there, but he left IBM a year or so before I joined. So effectively, I was a replacement for the kind of work that Jim was doing in the R-Star project. And R-Star was started by Pat Selinger, so she hired me. She was my first manager. And lots of other people came out of that project. Laura Haas and Hamid Paresh, Bruce Lindsay, all these people became IBM fellows also. Hamid Paresh is still there, but bulk of the people are now gone. Sadly, the emphasis on the hardcore database research has come down like crazy. In any case, we'll get into some of this maybe later, but I will also welcome you to go look at this URL. You'll see the links to talks I've given in more recently in both Japan and South Korea, as well as this week and late last week over here in Hong Kong. One of the talks is the data landscape, trends and directions. In today's talk here, I'm going to be restricting my attention to more of the cloud-oriented stuff and not as much about the broad-based stuff. And so, if you go to this URL, I didn't put a QR code for that, you will find the slides of this talk. If you see the PowerPoint slides in slideshow mode, you will see the slides I'm hoping to show. I might not get around to showing all of them. But if you go into edit mode, you'll see lots of other slides that are hidden. And so I try to make all of this available in the PowerPoint version rather than PDF and all this nonsense. So feel free to spread the word and all that. So like I say here, not all the references I've managed to put in. I keep adding stuff. So you'll find lots of hot links like this. When you are doing it in the slideshow mode, you can click them. Otherwise, you have to do Control C, Control V. So this reading list that I prepared for last year's course at NUS has a lot of interesting papers. Obviously, there are more papers that have since then come out. So you will see some references in the text of the slides themselves as I go on. And like I say here, I keep revising these things. So if you want to keep up with, if you get excited about some topic, for instance, one of the talks I gave at University of Osaka a couple of weeks ago was on query optimization, processing, trends and directions. So that gets into even more nitty-gritty stuff about query processing stuff. Like I said before, but Pat Selinger was the mother of cost-based query optimization. So that kind of work has gone on for a long time in IBM research in San Jose. And now, of course, there are a lot more places where people are doing all these sorts of things. So, so here's what I'm going to do. Instead of just talking technical stuff, it's important even for pure research kind of people to pay attention to markets and money and such with respect to market share and where the money comes from in the database area. So I'll show some IDC and Gartner kind of analyst information, then get into cloud environment, and then in general, and then specifically about users' expectations with respect to databases in the cloud environment. And then depending on time, I'll get into nitty-gritty about various systems that have been put out there. So here is the last 5 years story with respect to money, the market numbers, how much of it came from non-cloud environment and how much from cloud. Specifically database revenue, right? Exactly how they figure out all this, we don't need to get into. But in general, different analysts will have different numbers because there's a lot of subjectivity involved in deciding what is what and so on. So it's the trend that's more important than the actual absolute numbers. And look at this also. It shows the ranking of the different vendors. Sadly for me, the company where I spent so much time is now sitting in the 5th position. Even to begin with, in this 5-year history, it wasn't a great thing for me to see Microsoft and Oracle doing better than IBM, but it's now pathetic that it's 5th. Even Google has gone ahead of IBM. So the color coding is that if it's green, the position improved from year to year. If it's orange or whatever, it's coming down. So look at that. SAP got booted out of the whole top 5. And even Oracle has come down from 1 to 3 now. So the king of the hill at this point is Microsoft. And Amazon, of course, has moved up also. So there is this other chart that regularly is put out by Gartner. It's called the hype cycle. So the idea is that many specific topics, and they do it for various disciplines in computer science, but this one is for databases. Subtopics within the database arena will enter like that, and then depending on what that topic is and how well it takes up in the market, and also whether they deliver the goods or not, as opposed to just hype and then it disappears, it might ultimately come here. So initially there will be a lot of hype as time goes on. And so this is the height of peak of inflated expectations. And mind you, AI has gone through this 4 times or so now. The youngsters in here might think, oh, AI is all some modern, brand new, blah, 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 data learning, machine learning and deep learning and all that is the greatest thing since sliced bread. Even before I came to the US in '77 for my PhD, as an undergraduate student at IIT Madras, I already was tracking what the heck is going on in speech understanding and such at Carnegie Mellon. Raj Reddy, this Indian guy who later got the Turing Award, the only guy to get that. Crazy. Billion people each. We both have only one person each. And we are for Chinese, and Raj Reddy for Indians as the only Turing Award winners in these 2 ethnic communities. Anyway, so there were things like that were going on, but there was a lot of expectations that were built up with all sorts of promises, how it's going to replace doctors, this, that, right? Then they didn't live up to it. So then you get into this trough of disillusionment, and then after a while, things might still come out of it. In some sense, one could say AI has got a slightly better track record now, and so maybe it's somewhere here, right? But in the case of some of these topics, they just had a death before they reached this plateau kind of stage. So it's good to sort of keep this. And in general, I have a talk on careers and do's and don'ts and how to be successful and such, where I use my own life history, from my undergraduate days on, how my life evolved, what I succeeded and what I didn't, why I think some of those things happened and why certain things didn't happen, even though I would have liked them to happen. Again, you can find videos of that talk. I gave it in Fukuoka as well as in Pohang in South Korea just 2 weeks ago. And there you will see I talk about how, don't always get excited to follow the crowd, sheep mentality, right? There are times when you should do your own homework and figure out, even though tons of people are working on a topic, it's not that there aren't any other interesting problems to be solved. Sometimes the research community declares recovery and locking as a solved problem. That's what happened when I started working on Aries, right? Everybody was laughing at me. Why is Mohan wasting his time looking into recovery and fine granularity locking? And so turned out they were wrong. Even people like Jim Gray and Bruce Lindsay and such, who were questioning these sorts of things, didn't realize that by looking at things differently than what the System R guys had done, that something better could be produced, even though they had given up on fine granularity locking at the end of System R with right-ahead locking. They did it in System R for shadow page recovery method, but not for right-ahead locking. So stuff like that you need to keep in mind as you figure out what you want to do with your life and so on, whether you are in academics or industrial research. In terms of market share, coming back, look at this. These guys, IDC guys, estimated it to be $64 billion or $65 billion last year, whereas the Gartner guys had $80 billion. But as far as the split between cloud and non-cloud is concerned, it's about the same. Okay. And here you see, more granular information about individual vendors and how much money they made. So look at that. Alibaba is very close to Google. So 1.4 for Google, 1.2 for Alibaba. But according to this, SAP is much more than Google, whereas the Gartner guys kicked out SAP from the top 5, pushing them below Google. So there you'll see some inconsistencies like that, but don't get too excited. IDC also has done a forecast for the next 5 years, how much money will be there in this market and how much of it will be cloud versus non-cloud. And as you can imagine, the non-cloud part will be becoming bigger and bigger share compared to the on-prem. So that's another reason why there is unbelievable amount of activity now in taking previously existing systems and converting them to work in the cloud environment, or even developing from scratch, born in the cloud kind of database systems. So before I get into all that, you need to be aware of storage hierarchy like this. In terms of speeds, it's fastest access times at the top and very slow at the bottom. But in terms of cost per byte or megabyte, whatever you want to look at, it goes down dramatically as you come from top to bottom. And also typically the capacity amount of the thing that you can have will be a lot more. So hence this pyramid shape. And look at this access speed differences. To access something in a traditional disk that's not even remote, that's still locally attached to the CPU through a fast bus and so on, is 10 million cycles, whereas something that's in the register, in one cycle you can access it. So it's these sorts of things that make database people's life very interesting. When to store what, and if you have a pot of money, how do you split it across these different levels? How much of main memory are you going to have versus flash versus magnetic disk and things like that. And by the way, some of you might be thinking, oh, what is tape drives? That must be some Mohan, last century kind of thing. Guess what? Tape drives are still in use. IBM still owns that business, even though IBM sold the disk drive, both optical disks and magnetic disks to Hitachi many years ago, and 25% of my lab disappeared because of that. There is still hardcore research and product development work that's going on in IBM, and research is going on in my former workplace. In terms of, if you look at the typical way in which in the cloud environment disks are managed is to make them be across a network from the compute servers in which query processing and such things or the application might be run and so on. And so when you have this remote storage, it can be accessed at the block level as if it's like a local disk. It's like managing a raw disk kind of thing, right? Or you could go through a file system and use file APIs, which might be traditional file APIs or more these so-called object file systems kind of APIs. It's also called internet scale storage via APIs. And so there are examples shown in this slide on, in the context of Amazon, what some of the names are that they use. And then here you have for glacier storage, they call it. These are typically much slower but bigger capacity kind of things that you use, not so much for online data that's actively being read and written, but more for archival purposes. And then you have a storage gateway which allows you to combine data from the cloud and the non-cloud or on-prem kind of places where for security reasons you might not want to move that kind of sensitive data to the cloud, but you still want to be able to, in your own, the owner's applications, combine data from these two things. Because in doing all this, especially in the cloud environment, you have to worry a lot more about encryption, security, and all that. So that introduces lots of other things like, can I process queries against the data while it still remains in the encrypted form, or do I have to decrypt it? Equality predicates are easy to do with the data in the encrypted form, but if you want to do range predicates, unless the encryption is order preserving, you can't do it. And then people will tell you order preserving encryption is not as secure as non-order preserving. In terms of cloud models, you have the public cloud, private cloud. There's also a notion of community cloud where a bunch of customers in a certain domain, automobile companies, insurance companies, and so on, might have a cloud that's just restricted for their usage. And then you have this hybrid cloud that I already referred to, where you want to be able to combine the private cloud information with the public cloud. And IBM invested a ton of money by spending $34 billion to acquire Red Hat a few years ago, because they are considered leaders in this multi-cloud as well as hybrid cloud environment. The idea is that given that there are no standards in this world, in the cloud arena, Azure cloud of Microsoft is different from Amazon's AWS, which is different from Google's cloud. How do you make the customers become independent of these kind of dependencies? So they built a layer on top, if you like, and as long as you use their APIs, Red Hat's APIs, then you will be immune from the dependence on any particular vendor, because willy-nilly you could change your mind and move your data from one kind of cloud to another kind of cloud without your applications that make use of the data having to be changed. Okay? So there are these cloud deployment models. There's a little more detail about what was in the previous slide. In terms of the cloud service models, you talk about the infrastructure as a service, platform as a service, software as a service. It depends on, whether you use the capacity of the cloud, CPU, storage, and network in its raw form, and then you manage everything on top of it, the operating system, middleware, whatever. Or do you go to a slightly higher level of abstraction and then use the platform as a service, and the examples you will see on the next slide, where certain pieces of software that run on that kind of raw platform here will already be provided by the cloud vendor. And then you'll use their operating system API and such things, or even the middleware if database systems are running here. So you'll see this terminology of database platform as a service, DB PaaS. That's the revenue that's counted as being more truly cloud DBMS rather than somebody just running the pre-existing on-prem version of DB2 or SQL Server on this kind of infrastructure as a service. That's still not counted as cloud database revenue. What happened? So the top one is where application packages like SAP R3 and so on will be run. So here are some specific examples of the kinds of things. Microsoft Office and such being run at that level. Software as a service. The fourth one that's not shown in the previous slide is what's called function as a service, where are also known as serverless computing, where people want to run their applications. Customers wanting to just run their applications themselves and relying on the cloud vendor to provide the rest of the stuff, high availability, this, that. And so as an example, this AWS Lambda and Azure functions. In terms of failure tolerance and all that, you might have a primary data center and then a backup data center, and depending on the kinds of failures you want to deal with, this other one could be, let's say, in the same area, meaning like San Francisco Bay Area, both are there. But what's the problem with that? Our area is earthquake prone, so if a big one does happen, as people have been forever predicting, it will wipe out both of them. So for that reason, typically, this should be kept farther away from this, thereby reducing the likelihood of simultaneous disasters like that, flood, earthquake, and so on, or even terrorism and such things. And so you can talk about the live data being replicated as well as the backed up data and such also being backed up. And so that will happen at different levels in the stack. And exactly how you replicate the data in this kind of scenario, especially for the online data, there are various approaches depending on whether it's the same database software that's running in both places, or it could even be different. You could have DB2 here, you could have Oracle here. And so whether log records get shipped from one place to another, or maybe queries that are generated from the log records at this place then get sent there, is all further discussion about the pros and cons of doing it one way versus another way. And then the vendors also talk about, within a data center you could have multiple racks, which all might have the same dependency in terms of power supply and network capacity and so on, network linkage. Whereas if you have this kind of notion, multiple data centers, they have more independent way of getting powered and getting hooked up to the telecom vendors, networks, and so on. So this increases the availability. So typically you'll hear about, I didn't say it in my earlier slide, maybe I'll go back there for a bit. Yeah. If you look at this, they talk about 11 nines availability, 7 nines availability, and all that. What does that mean? 99 point, so already 2 nines have been counted for. How many nines appear after the decimal point? So the fancier your tolerance is, the greater will be the number of nines. So 99.999 will be 5 nines, whereas if you put more nines, it means even more reliable. So in order to do all that, you need to think about these sorts of things, the notion of data centers which constitute together an availability zone, and then you have multiple availability zones which might be spread across, let's say, US and Europe. And then on top of all the regional ones, which may be North America, South America, or different countries within the same region, you also have to worry about what is called data sovereignty. The Chinese government might not want Chinese citizens' sensitive information to be stored outside the physical boundaries of China. So that also causes grief with respect to when you are dealing with a distributed database, which piece of data has to be resident in which portion of this wide area network and such things. And GDPR kind of regulations also play a role in such things. Traditionally, if you go back and look at non-prem environment way of architecting big database systems with lots of data, we have talked about shared nothing architecture versus shared this architecture. And here, the database gets partitioned, and each partition is attached to a node, and so that owns that data. So if anybody else running an app running in node 2 wants access to data owned by node 1, that request will go from node 2 to node 1, and that will fetch the data with applying predicates, whatever, and all that subsetting, and then send it to the guy. Whereas in the shared disk architecture, all the data is equally accessible for read and write to all of the nodes. And this introduces different kind of complications than that one. So I can spend many hours talking about this being one where you need two-phase commit if a single transaction touches data in multiple partitions and modifies it. Whereas here you don't need two-phase commit, but then in order for multiple nodes which may be simultaneously trying to muck around with the same data, now you have to do locking at a global level, meaning the locks cannot just be localized to the individual nodes, and they can independently keep granting and freeing locks for transactions running in them, but they have to coordinate across the nodes, otherwise there will be chaos. The reason I'm pointing out all this is in the cloud environment, these same problems crop up, and so far people have mostly taken the shared nothing approach with some backups for these. Node 1 there will be one prime or one double prime, which is the backup for node 1, and for node 2 similarly, and so on. These backups are not able to do simultaneously updates with the primary. They are there maybe supporting reads but not actively updates. Only if the primary goes down, then one of those backups, one prime or one double prime, will become the main primary now, become the primary, and then the remaining guys will still remain as secondary or backup guys. And I personally worked on something called coupling facility, which was the version of DB2, which was more super duper than the plain shared disks where you had page address full storage and such. And that was a leg up that we had in IBM with DB2 compared to Oracle with its RAC that you might have heard of, which was all, we shared this way of doing things which was different from the shared nothing done by Teradata, for example, or the likes of Jim Gray and Dave DeWitt and so on, were big proponents of shared nothing, whereas guys like me were in favor of shared disk. It's more and more looking like in the cloud environment, shared disk is what's going to win out. I got more details here, but I don't have the time now to go through this. I'll let you go independently look at some of this. Turns out in the case of IMS, they even had a relational hierarchical database system, the ability for two nodes to have equal kind of access to the shared database, but not n nodes. So that was very limited. More recently, Aurora guys in Amazon have done something which is just this two-way sharing, 40 years after the original thing was done in the hierarchical database context. So there's also this discussion, so I mentioned R-Star here, which I joined as my first project, in the context of which a few things got done. And replication also, there's always this debate about synchronous way of replicating data from the first site where within a transaction you make a change and you propagate it to the other copies of that data before you let the transaction commit. That's synchronous, versus you let the transaction commit after it modifies the primary copy, and then outside of that transaction path length, response time, you actually update the other copies, which means that the other copies are not continuously in sync, but there is a delay, which is similar to the way warehouses have worked. You have an OLTP system, you have a warehouse, which is a replica of what's in the OLTP system, online transaction processing versus online analytical processing. And periodically, in a batched way, you send the changes happening in the OLTP to the backup, to the OLAP system, the warehouse system. And then analytics is done here, which means it will have less interference from these online transactions, but then it's going against out-of-date data. So HTAP systems are now trying to let you have the cake and eat it too. In the same database system, have OLTP as well as OLAP. This is the so-called hybrid transactional analytical processing, HTAP. So, surfacing back up a bit, every 5 years a group of database researchers get together, self-appointed, and it's been going on since 1988. I had the privilege of being invited to this August gathering only in 2018 for the first time. And so we had a meeting in Washington State, University of Washington in Seattle. And you will see the report linked to there, the output of that group. But more recently, actually, a summary of this report's findings are in the August issue of CHCM, my first ever paper with my name that appeared in CHCM. But there were subgroups within the gathering, and the subgroup that I took part in on cloud data services, we scratched our heads about what are all the important problems to be solved and why certain things need to be done differently in the cloud environment compared to the on-prem environment. And so those are some of the things that I mentioned here, which have to do with things like, in a traditional IT shop, you have a lot of well-paid, whatever people, a lot of intimate knowledge that they have about database systems and even their internals, and hence they can be relied upon to do tuning of installation parameters and ongoing tweaking of various things like how big should the buffer pool be and when to reorg and when to do backups and all that sort of decision making. And if query plans generated are not good, try to go figure out what the heck happened. Is the optimizer messed up, or some statistics need to be manually tweaked in the cost model business that I referred to at the very beginning. But these sorts of things are expensive, time consuming, and you don't have enough resources of that kind available, even if you have the money, because there are only so many people like you, and so as IT gets into society more and more, you need more of these people. But the value prop of the cloud is, pay as you go, no capital investments, you don't have to have staff of that kind in your own organization, blah, blah, blah. So, and the cloud vendors are also competing with one another. So even though they may be big guys like Amazon and IBM and so on, they also want to minimize the cost of providing whatever they are providing to their customer base, right? So they are all, as a result, equally wanting to automate more and more or make things self-tuning and so on, which is where all the hoopla about AI comes in. So you'll see in my other presentation that I gave in Osaka, the discussion of various query optimization and query processing technologies that are getting highly influenced by now deep learning and other things. When to create indexes, and even the creation of the index, so-called learning indexes that Tim Kraska and others have worked on at MIT, have to do with not necessarily indexing everything for all key values, but only a subset based on access characteristics and the dominance of certain values versus other values and so on. So you'll see all that. One of the conclusions of the group was, while there are lots of OLAP kind of systems, analytics systems that are even open source, in the much more time sensitive and performance sensitive OLTP distributed databases, there aren't any really good open source systems. And the other problem that's gained a lot of attention, if you look at products like Amazon's Aurora and more recently Google's Alloy DB that was announced earlier this year, their goal is to say, how can we help people who already have MySQL or PostgreSQL kind of applications that have been running not only in an on-prem environment, but even single node of such clusters and such. How can we, without requiring changes to the application, magically let them, just like that, run on the cloud, thereby gaining the benefit of massive capacity for storage as well as computing and networking and so on, but also providing the much higher reliability than 11.9s and all that I mentioned before. So it's in that spirit that I will quickly tell you what some things are that are going on. Here also you worry about the data sovereignty that I talked about earlier, and as the depth increases in the storage hierarchy, how to accommodate all the glacial storage and things like that. And so here things like auto scaling, pay per use, and predictable costs. That's the other thing. See, people don't want to, when they are using a utility like, let's say, water supply or power in your daily life, you want to know ahead of time how much it's going to cost. In a similar fashion, in this context, when you issue a query, you don't want, after the fact, that system coming back and telling you, guess what, you ate up so much resources, here is this huge bill. You would like to know ahead of time a bit of an estimate, or you need to be able to tell the system, do your optimization so that only this much money is spent on the actual optimization and the rest of the money is going to be used for the execution. You'll hear in my other talk, you don't want to waste your time optimizing like crazy if any odd way of executing that query is going to cost less than the amount of time you waste and resources you waste in doing the, let me try out all possible ways of executing the query and things like that. And there is also this whole business of serverless that I talked about, function as a service. Those sorts of things are also things to worry about in this context. And so I've already mentioned some of these other things, and also how to run multiple customers' workloads in the same database system, while still guaranteeing certain comfort factor for them with respect to that their data is secure and their competitor who might be using the same cloud doesn't sneak into their secret data and so on, right? So questions like, even if there is one instance of SQL Server running in the cloud, should the different customers' data be in different databases under that one instance, or even in the same instance of the database, not database system, you can have multiple customers' data, but they will be made disjoint by making use of different tables for different customers' data, or could even in a single table you can intermix different tenants or different clients' data. And there are various pros and cons that you can come up with respect to the different choices. And even questions like this, when is it beneficial to move to the cloud versus when it is not? From a money perspective, performance perspective, can you develop tools and methodologies to help the C-suite kind of people, CTO and such, CIO, more clearly have a quantified way of making such calls? Because there's always, various things that you can throw around, elasticity and higher reliability and ease of access from different parts of the world and so on, but then some of it comes with other headaches also, the likelihood of hackers getting in and so on. So I already mentioned HTAP. So everything that has been talked about in the past in the context of on-prem database systems, they rear their head in this context also. Should I store the data in a row-oriented fashion or in a columnar fashion? Row-oriented is better for OLTP versus columnar for OLAP. And these things get complicated if you want to permit both kinds of workloads against the same database. because you want to have your cake and eat it too. So data typically in these situations is made to enter the system in a row-oriented way, and then gradually, as time goes on, in a batched way, some of this data will get converted to the columnar form, things like that, okay? And this notion of disaggregated storage, which I'll get into soon. So there's a long list of database systems that fall into the category of cloud database systems. So what's the difference? If you look at a traditional database system on-prem versus, let's say, a cloud one, you see this arrow, it's thicker here and shorter. What does that mean? Bandwidth is higher and the access time is less. Whereas this arrow is thinner and long. So you are accessing storage across the network. This might be just still taking the same stack, but instead of keeping the data in a locally, in a high bandwidth way attached storage, you are now moving it across the SAN or even a wide area network, right? But this would be just everything else being the same. And then you'll now come across the twists that come with this. So what's happening here? The on-prem architecture, the storage alone being separated, and then comes this state separation approach or stateless compute, where there is only the cache that is running on one or set of machines, and then the rest of the stuff will get pushed down to the so-called storage servers. This is what's called the storage disaggregation, because while the size of the data and all that is fairly static, and even if it changes somewhat gradually, the query workloads on the other hand could dramatically change. Whatever the China thing is that happens in November, this big shopping thing. Yeah. So those sorts of things really throw a monkey wrench into your traditional way of doing things, right? So this whole discussion about various systems and how they've adapted to the cloud has to do with how do you accomplish this, whereby the set of nodes that are at any given time attached to a certain database data that's in the storage servers keeps changing. And so, for instance, these guys, they have a pool of instances that are already warmed up. The problem with some of these sorts of things is, if you say dynamically I'll allocate machines for compute and such, it might take a while for those machines to come up to speed in the sense of the database software instance having to be installed on it and so on. Apart from the fact that even if they are already pre-installed and they are just sitting there waiting for work to be assigned to them, their buffer pools are empty. And so now if you start processing queries on them, ever so slowly the data that these queries access will get brought from the storage servers and so on. So in order to deal with all this, various tricks have been played, but the basic idea is still to guarantee the elasticity aspects of the cloud way of doing business, whereby you as the user of such things are not pre-committing whole lot of resources by buying hardware and such licenses for the software, so-called capital expenses. Instead, it's only the operational expenses, pay as you go stuff, that's the value prop of the cloud way of doing things. So these guys initially targeted the MySQL on-prem applications to be magically moved into the cloud, and later they did it for Aurora. For Postgres. This was the Aurora project of Amazon. They got the systems award and all that. So there are more details in these slides as to what they did and how they did it and so on. So they moved the logging and the storage, applying the log records produced in the compute nodes to the stored version of the data to the storage node. These guys produce the changes and such, and they might even apply those changes. They will apply those changes in the buffer pool version of the data that they have in their cache, but the persistent stored version is independently modified by log processing agents sitting in the storage area. And there are more pictures here that will get into some of these sorts of things. So if you notice, it says primary read-write database, and secondary read only. So you can post queries here, but even to make those queries see a consistent state of the database, they rely on things like versioning the data and applying the ideas of snapshot isolation and so on. If you have only a single copy of a piece of data and you do in-place update and you destroy the previous version of the data, then over time stuff will keep coming here and it's sort of not mutually consistently updated to the most recent version that's on the primary, and so you might see some inconsistencies. You might see a child record, but the corresponding parent is not there because these two things got updated slightly out of sync. Whereas in the primary node, because of referential integrity and all that, you'll always be guaranteed that you won't have such orphan children, for instance, when you do the read. Stuff like that. I'm getting into more details than you probably care for. So they have this notion of a head node where they do a bunch of stuff like traditional full-blown database system node, but they don't deal with the actual storage, the persistent storage, where the data is going to be kept for the long term. And so this one, it magically moved. So anyway, producing the log record, even if transactions have to be rolled back, undoing the changes and so on are still done there. But when it comes to the storage area, over here, it's the storage servers that will do the job of reading the pages back into their buffer pool and applying the log records that came from the compute nodes, and then also dealing with, in this way, multiple copies. So for instance, in their case, they maintain for each piece of data 6 copies across 3 availability zones. They figured out that that's the best way of guaranteeing the kind of number of 9s that they wanted to support, right? And they do this 4x6 write quorum. I'll let you go read the paper cited there for more of the details about all this. But they also apply parallelism in applying the log records. Otherwise, the storage server nodes won't be able to keep up with the rate at which log records are being produced. But they also have to guarantee that in whatever order processing was done here is not modified here. So you can't, reorder the update to a piece of data. First update happened and then the next update according to the master. But if you flip them around, then you'll have an, disastrous state of affairs. So all of this is, if you read Airy's paper, you'll see some of this. As long as you keep the order the same as you apply log records for each page, across pages you could do them even out of sequence, but that's okay. But within a page you have to keep the order. So there are more details here. I won't take the time, but it shows, for example, how the storage node processes the lots of log records that are showing up that relate to the data that it's responsible for. In a sense, it's like shared nothing at that granularity, right? But at the level of the compute nodes, it has access to all the data. But for the time being, they are restricting that compute node to be one, and that's the only one that can update the data. The other nodes are read-only nodes, compute nodes, and they can process read-only things, and one of them might later, when this one update node fails, take over for updating. They also decided, instead of dragging all the data up to the compute node, to apply, in the case of analytic queries, all the predicate evaluation and so on, which could cause a lot of traffic across this network. Why not push down the predicates and make the storage nodes do more than just supplying pages to the compute nodes? Instead, it can supply the selected records that satisfy the predicates that are being posed, and the rest of the processing, unioning this information or doing joins and so on, will still be performed at the compute node. And this is the Mickey Mouse two-way sharing that was done, which I said is similar to what IMS did more than 40 years ago. Justin Lewandowski did this, and they are not sure that this was a good thing to have done. It's also very weird in the sense that between nodes, it will do page level conflict detection, whereas within a node it will do record level, which is another twist. So Amazon also, of course, apart from all this OLTP-ish kind of stuff, has had a separate product called Redshift, which is essentially the warehouse on the cloud, which is similar to the other one that's become very popular, at least in terms of money making and going public, which is Snowflake. Okay, and so anyway, this one has been around for a while, but more recently they've done some innovative stuff in this context that I won't have the time to go through. But this is the kind of stuff that my former colleague Hippocrates Pandis has been working on, and he gave a talk even at this year's BLDB, where I was the industrial program chair, and I invited him to give a talk in a manner somewhat similar to what Amazon guys did to make on-prem stuff become suddenly running on the cloud and benefiting from all the cloud stuff. Unlike them, where they did it for MySQL and PostgreSQL, these guys, they just took their SQL server that was on-prem and they modified it to run in the cloud. There are many similarities and also some differences. In their case, they said the compute nodes, if they fail and when they are brought up, they would have to re-establish what was in the cache, and for a while they'll have a lot of faulting happening where they have to wait for the data to be brought from the storage server. So they said optionally they could even dump the contents of the buffer pool in the compute nodes every so often to persistent store over there, but that's just still a temporary version of the persistent data, but it's not the ultimate version. That's not the real truth. It's just a not a hack, but an optimization to, when you fail and come back up, quickly reload that data and then you'll get going. But you have to now verify that while that node was down, some of that data hasn't changed, and if it has changed, invalidate the version that got put on the secondary store. So there are more details here as to how they do things, where the this read-write node might have modified something and then sent the log records to the storage node to process. Meanwhile, somebody else asked for the same page for reading, and they want to see the more recent version, not the old version that they have. And if you go ask this storage node, it better not grab that page from disk and give it, because in between some other changes had been done and their log records are sitting there yet to be processed. So you have to know exactly what the story is of the pending log records that need to be applied versus this request that has come in, whether there is any connection between them, or you can supply this page without worrying because the list of log records to be applied doesn't apply to this particular page. They have some other page and so on. So there are more details here about all this. And Google has many database systems. Originally, the way Google, Facebook, and all these guys developed their database systems, they were intended purely for their own internal users, what Google calls product areas, search, YouTube, maps, and on and on. There are various things, right? It's only in the case of, and in the case of course, Facebook, they open source some of their things, even though they didn't offer them as services that they will have in their cloud and so on, and let outsiders make use of their services like Google Cloud. Whereas Google Cloud, when they established that, suddenly a subset of the systems that they had been using for a long time, like Spanner, for example, they decided to make them available to random people across the globe, as long as they pay, obviously, on their cloud. Okay, so this is when the jury was out for them to now say, oh shucks, we did certain things that our own population tolerated. Now I'm addressing this heterogeneous crowd outside. They will compare us with, Amazon and others. So we better worry about how easy our things are to use, what kind of tools we have, and how much they cost in terms of performance as well as money, on and on. So it's in this spirit that I've been telling them they have to go out and give talks and they have to establish their identity and make their products be compelling for others to benefit from and things like that, because there's going to be now this kind of comparison that's going on. In this context, Alibaba and so on are doing a fantastic job of writing papers, not just research papers, even industry track papers on their products. There isn't enough of that being done by Google guys, for instance. So there's a lot of stuff that you need to think about as individuals, once you get out into the real world, as to what kind of career you want to have. And so I talk about some of this in that other presentation I mentioned. So here they have relational as well as NoSQL and even specialized in-memory database systems. And so it's in this context that Spanner was developed eons ago, and I thought for a long time, until I started consulting for them, that it was just sitting in the back burner. But guess what? It's being used like nobody's business inside the company. But they haven't been making enough presentations, doing enough presentations to the outside world to let them know. So one of the other invited talks I had in Sydney at BLDB was by a guy from Google, and I asked him to talk about the historical stuff rather than just the nitty-gritty about one system and so on, one algorithm. And so I'm saying, hey, you did certain things in a very unique way and all that, 5-way replication across the globe, and they were arguing many years ago why it's important to do synchronous replication rather than asynchronous, because asynchronous can lead to concurrently in multiple nodes people doing stuff that ultimately you will discover were conflicting, and then you have to take screwdrivers and this and that and figure out how to reconcile. The smart-ass people even in Google, in their own product areas, figured that this is too much of a headache to deal with for them, so they argued in favor of synchronous replication, even if it means that the response times are increased and things like that. And they also made use of GPS and atomic clocks and all that to do synchronization of the parallel activities across the whole globe, right? Your database can be that distributed in their way of doing business. To begin with, it was a very low-level kind of thing, and then they came out with SQL support through something called F1. There have been papers written on these things at BLDB, Sigmod, and so on. The more recent thing is what I told you before, which is analogous to the Aurora kind of work that AWS did, where unlike Aurora, where they went for MySQL first and then these PostgreSQL applications, these guys have gone straight to PostgreSQL. Similar idea that you want to take existing apps and move them to the cloud and get all the benefits of the cloud without having to rewrite anything. But these guys also have put a twist. So they've introduced some of the HTAP-like functionality by saying, through the magic of AI and so on, they can now help the customers without the customers having to make the call as to for what portions of the data that are in the row form, optionally columnar versions of subsets of the columns within a table can be maintained to improve the speed at which analytic queries can be processed. And so they also further have said something called Vertex AI that Google has, invocation of some of the models associated with some kind of use cases. Instead of requiring the data to be extracted out of the DBMS and fed into that thing, they can even, like user-defined functions, run some of these AI-ish algorithms within the DBMS itself. From your SQL queries, you could even, like UDFs get invoked, you can invoke some of these AI-ish things. So I don't have enough time to go through all this, but there are more slides here that I'll let you go look at it. And of course, the multi-zone and all that high availability stuff is also there, how many copies you maintain and exactly how they are managed. They even talk about, unlike in the case of Oracle's database in memory, which is a HTAP system, where the users get to decide for setup tables which subset of those row-oriented persistent tables for which you want to maintain in-memory columnar versions of all the columns of those chosen tables. So if the node goes down, then all those in-memory things will disappear because it's non-persistent memory. And then they would have to re-establish those columnar versions, and they use replication ideas to keep the columnar versions in sync with the row-oriented, because all the updates are actually being applied only to the row-oriented version by the app itself. It's subsequently that replication then propagates those changes to the row. But these guys are talking about, so in the case of Oracle, the query optimizer, based on your consistency requirement, that might decide, instead of processing the query against the row version of the data, it will process it against the columnar version. But it will choose either this or that. But these guys are even talking about, in parallel, even using the row version as well as the columnar version in a tricky way and so on. So remember, I said there aren't enough OLTP systems in the distributed context in the open source arena. That's still probably the case. But meanwhile, there are these startups that have been, hard at work doing OLTP across the cloud and so on. This is even before things like Spanner that Google did, which was originally being used only internally, came to be available through the Google Cloud. The startup CockroachDB uses a shared nothing architecture. They have limited kind of consistency support that they have. They are only serializability, non-snapshot isolation, and they support as their API PostgreSQL. And instead of doing their own storage manager, they've chosen to use some open source thingy that's there, either RocksDB or Pebble storage. So you'll see more of these sorts of things happening where people rely on somebody else's key value store or whatever kind of thing, and then they build fancier functionality, a more relational kind of system, and so on. And Snowflake, I already very briefly mentioned. It's the warehouse on the cloud, similar in flavor to Redshift. They went public and tons of money went the way of the founders and early employees. So a lot of these very successful companies, in terms of not necessarily making profits, but finding investor money, either by going public or even before going public, getting investments from the VCs of my neighborhood like Silicon Valley or people elsewhere, sovereign funds of, Qatar, this, that, UAE, and so on. They are now after talent. They are raiding the likes of Amazon and IBM and Google and such places, Microsoft, to get the smartest and the brightest of people into their employee ranks. Alibaba, in similar flavor to what I showed you before with Google, has many kinds of systems that they make available through their cloud. And when Feifei went there, he seems to have triggered an avalanche of papers to be written by these people. So this year's VLDB, 22 papers we selected for the industry track out of 60, I think, that were submitted. And 5 or 6 of them are Alibaba papers. And 2 were from ByteDance, what is that app called?
TikTok.
Yeah, TikTok owners. And so it's sort of exciting to see we are talking about industrial track, not research track, right? Even there they are cranking out papers. And so you have systems like this where they are doing some kind of hardware, software, core design type thing, where they're trying to make use of flash and even FPGAs and GPUs. And one of the problems with flash is that you can't do in-place writing. When you read a page and modify it, you have to write it somewhere else. And then you have to garbage collect this old version once you know that it's no longer needed, even if you're doing data versioning and so on. So you have to keep somewhere this mapping from a logical page to the physical location where it resides. And over time that changes, and for a while you have to track the multiple copies you might have. And so they talk about where they keep that and so on. So the Polar file system has added capabilities now to push down predicates and things like that, and also to support these different kinds of devices. And in a similar fashion to what I showed before for Aurora, parallel scans being done by pushing stuff to the storage layer. These guys are also doing similar things. And then they're also trying to improve access from one machine to another machine by doing stuff like exploiting RDMA, where one system CPU can directly, put its hands into the other system's memory and grab stuff. Of course, you have to worry about security and all that in this case. But they are relying on shared storage as well as shared nothing concepts. And this is the last but one slide. So I made a presentation earlier this year at a workshop attached to ICDE 2022, which was to have been held physically in Kuala Lumpur, but became virtual thanks to COVID stuff, where I argued that the shared disk architecture that some of us worked on, that was dissed by the likes of DoIT and such, because they were favoring shared nothing as done by Teradata, non-stop SQL of Tandem, and some other products, as well as, more importantly, research projects like Baba at MCC and something else at Wisconsin. I had said that if you want to allow multiple compute nodes to simultaneously have the ability to read and write the same piece of data in the cloud context, you need to now adopt and adapt the stuff that some of us worked on that has been incorporated into Oracle and DB2 and so on. And so I said it's important for people to go read up on, what all we did and why we did what we did, where it works, where it won't work in the cloud environment. And so you can go listen to that presentation and so on. And this is just a repeat of the first slide in case some of you didn't copy the URL or whatever. So thank you.